Okay, we're ready to go.
Ok, bueno, bienvenidos a todos a nuestro evento de Biomasa 2020. En virtud de que tenemos unos cuantos participantes que no hablan español, entonces voy a hacer la presentación del evento en inglés. So, welcome everybody to our Biomass 2020 webinar series. We want to thank everybody for being here. This was an event that we were initially going to have, face-to-face, but of course, because of the current situation, we've decided to take the opportunity to do it online and kind of also not to waste this time and continue with the plans. First of all, I would like to ask everybody to put your entire name, your first name and last name, so that we can have a registry of all the participants and to generate the how do you call that? I went blank. The certificate. I'm sorry. The certificate. So this is an event that we started back in 2017. It was at that time it was actually a technical course that was funded by the United Nations University, the biotechnology program for Latin America and the Caribbean. This time we have decided to make it as a well, it was planned as a conference, not as a webinar series, and the purpose, there are two different purposes. We've decided to raise a little bit of awareness about biomass valorization in Latin America, not only in Ecuador, building a little bit of community. I mean, there are many people who are working on biomass in Latin America right now, so we would like to get a little bit closer to everybody. And I know that not all of them are here, but we're hoping that through the people who are participating now, the message, gets shared and we get more people in time. And also to reflect a little bit about the possibilities of biomass valorization and how that can impact the economic model and the bioeconomy perspective in Latin America. And lastly, I wanted to introduce us a little bit. This webinar series has been organized through chemical engineering and mechanical engineering. We have the Institute for the Development of Alternative Energies and Materials, which is the one where most of us are. We have different research lines in bioprocesses, especially anaerobic digestion, bioethanol, organic acids. We also have a biomaterials line and thermochemical processes also, especially cracking and biomass pyrolysis. We also have the participation of the newly formed Materials Institute in Mechanical Engineering. And with that, I want to welcome everyone without, and I don't want to forget about this, we also have a call for papers, and I want to share a little bit the website of our So this is our journal. It's called Avances en Ciencias e Ingenierías. We want to welcome everyone to submit an article. We're planning to have a special issue on biomass. We want it to be published in December, so we have a deadline for August 18th. So if you need more information about the process, or you can visit the website, but you can also contact us through our emails that we have in the biomass art. And with that, I want to give you the chance to present Dr. Brown. Juanse.
Okay, thank you very much and welcome everybody. I am honored to introduce Dr. Robert Brown. He is the director of the Bioeconomy Institute in Iowa State University. He is the Ansel Marston Distinguished Professor in Engineering, the Gary and Donna Hoover Chair in Mechanical Engineering. He's a professor in Mechanical Engineering, Chemical and Biological Engineering, and also Biosystems Engineering. Dr. Brown is the founding director of the Bioeconomy Institute, which coordinates ISU research, educational, and outreach activities related to bio-based products and bioenergy. He also helped launching Iowa State's Biorenewable Resources and Technology graduate program, which was the first such degree granting program in the United States. He has published multiple books and journal articles, and his work, according to Google Scholar, has been cited more than 22,000 times, so that's a lot. About his education, he received his bachelor degrees in both mathematics and physics from University of Missouri, and then from the University of Michigan State, he received his master's and PhD in mechanical engineering. His research areas in which he has a lot of interest are thermal deconstruction of lignocellulosic biomass, biorenewable resources, biofuels and biopower, and process intensification, among others. So with that, I welcome Dr. Brown and thank you for being here with us.
Thank you, Juan. Can you hear me okay?
Yes, we can hear you.
Thank you for this opportunity. It's a real pleasure. I'm going to see if I can't share my screen, make this work appropriately. Can you see my screen?
Yes, we can.
Very good. So the title of my talk is Heterodoxy and Fast Pyrolysis. And you might say, what in the world is heterodoxy and fast pyrolysis? I didn't think this was a political discourse. Well, by orthodoxy, we talk about what is the accepted way of doing things. And in fast pyrolysis, there certainly is a heterodoxy, and that is you exclude oxygen from a reactor and you don't produce sugars from pyrolysis. And so this is what I'm going to set out in this talk is the heterodoxy of actually doing these two things. So with that, let's just go through this, this list of orthodoxy as it currently exists in fast pyrolysis. The first thing is how pyrolysis is defined, and that is the thermal decomposition of organic compounds in the absence of oxygen. And you say, well, who says that? Well, I'm going to quote a book called Biorenewable Resources, Engineering New Products from Agriculture. And as Juan knows, I was an author on that book, so I'm part of the orthodoxy in pyrolysis as well. The next orthodoxy is how we define what the products of pyrolysis are. And these are traditionally described as bio-oil, biochar, and non-condensable gases. And again, you can go to the source Biorenewable Resources and see that's how it's defined. And finally, the question is, well, how do you define bio-oil? Oops. Well, bio-oil is also defined in Biorenewable Resources as an emulsion of lignin-derived oligomers in an aqueous phase composed primarily of carbohydrate-derived compounds. And I have not set out these, what I would call the heterodoxies of pyrolysis in a textbook. I'm not that bold, but I'm bold enough to present these ideas to you in this seminar this afternoon. So let's now look at what those heterodoxies are. All right, that's me with the square head in the middle. And I've got three things I'd like to suggest in terms of these various definitions. And the first is, let's look at a different way of thinking about pyrolysis. I'm going to say it's the thermal decomposition of organic compounds, and a little oxygen is just fine. I'm going to define the products of pyrolysis as, well, let's add sugar among the major products. And then finally, the definition of bio-oil and the production of bio-oil. Why would we even want to produce such an unstable emulsion? So that's what I would like to discuss today, is these three ideas. Well, I thought I'd start out with a joke, but I haven't been able to finish this one. A scientist and an engineer walk into a bar. So what do you expect in that case? I'll just note the difference between a scientist and an engineer. I'm an engineer, but I'm not going to say that my view of the world is superior to that of the scientist. But I would say a scientist is characterized by someone who asks a lot of questions, and sometimes they can be annoying in the number of questions they can ask. By the same token, the engineer might be thought of as somebody that solves problems. And from the scientist's perspective, this can be annoying because often a scientist is solving problems before answering all the questions. So you decide where you fall in the camp. I tell my students, one will remember this from the days he was at Iowa State University, an engineer often has to think like a scientist. And so I'm going to pose a number of questions around pyrolysis, but I'm also going to talk about how an engineer might solve the problems that are posed by the questions asked and answered by the scientists. So with that, and so you'll notice I'm going to use these two icons shown here. The first one is the thinker with a beaker, a flask above his head. That's the scientist thinking of great questions. And the next icon you'll see on slides is that of an engineer developing solutions to some of these problems. So let's start with, why do we exclude oxygen from pyrolysis? Well, the fact is combustion happens. I've written out here the equation for the reaction of what's called levoglucosan, C6H10O5. We'll talk some more about levoglucosan as we go along. And it is a carbohydrate, and if it's combined with oxygen, it will burn and produce oxygen and water. That's assuming we put enough oxygen in the system. And that clearly is not a good thing, to take a valuable biochemical and just turn it into water and carbon dioxide, unless your goal is simply to produce thermal energy, and sometimes that is. Now, there are mitigating factors that are going to reduce this combustion phenomena so that we might end up with a happy result after all. So these mitigating factors include operating at low equivalence ratios. And by that, I mean, I've written here the stoichiometric reaction for combustion. And we can see it takes 6 moles of oxygen to completely consume this mole of levoglucosan. But suppose we ramp that down to only 1 mole of oxygen, or even less than 1 mole of oxygen. We will not have enough oxygen to completely convert to or reactant to these carbon dioxide and water. And we'll refer to that as low equivalence ratio, with an equivalence ratio of 1 representing enough oxygen to completely combust the fuel or the compound. Another mitigating factor is pyrolysis is operated at temperatures much lower than traditional combustion. We're talking typically no more than about 500 degrees centigrade, maybe a little bit higher than that, whereas combustion can occur at over 2000 degrees centigrade. So that is going to change how fast oxidation occurs. And in addition, at this lower temperature, there's going to be variations in reaction rates among the pyrolysis products. It's going to be a strong function of the activation energy associated with each of the reactions. And as we dramatically change temperature, we could dramatically change the relative rates that occur. And so if we're lucky, we might find that by adding oxygen at low levels, at low temperatures, we might have some results that we actually like. Well, what is the upside of adding oxygen? We saw that it could have some big disadvantages. Well, oxidation is, as far as I know, is always an exothermic process. So we're going to be able to release energy, and if that energy could be used to actually provide the enthalpy for pyrolysis, we're ahead. Think about all the difficulties that are done in practice to try to get enough thermal energy into a pyrolysis reactor so that those reactions can proceed. Putting oxygen in the reactor could increase the rate of, could produce exothermic energy release right in the reactor. And if we can do that, we can eliminate heat transfer from the process, And this makes our reactor much simpler to design and operate. And I'll talk a little bit more about that as we proceed. And finally, it wasn't until we started doing that I had the epiphany that heat transfer is an incredible bottleneck to process intensification and pyrolysis. And by adding oxygen to the reactor, we can eliminate this heat transfer bottleneck. Here at the bottom of the page, I'm showing you the notion of equivalence ratio. And combustion is going to be 1 or greater than 1. Gasification is usually equivalence ratio 0.2 to 0.35. And I'm giving the story away a little bit, but when we do so-called autothermal pyrolysis, where we admit oxygen in the reactor to an amount, to a level that is able to provide enough exothermic energy release to drive the pyrolysis reactions, this is typically at an equivalence ratio of 6% to 12%. And of course, conventional pyrolysis is 0% equivalence ratio. In other words, we don't put any oxygen in the process at all. So what we're going to try to do is, instead of working real hard to get heat transfer through the wall of the reactor or carried in with granular material, we're going to eliminate all that. And we actually want an adiabatic reactor in this case, because now the energy that we need for pyrolysis is going to be generated right in the reactor with the biomass. And in fact, what we're doing is we're consuming either part of the biomass or part of the products of pyrolysis in the reactor. Now, when we started thinking about this, we realized that there were some special considerations that we were going to have to put into the design of a laboratory scale autothermal reactor. I'm going to get into some more detail of this as we go on, but to do these experiments, we needed to be able to simulate adiabatic operation. And anybody that's ever tried to build a pyrolyzer knows that it's not only hard to get heat into a reactor, it's hard to prevent heat loss from the reactor as well. So we set up our system. Here's it's a fluidized bed system. We set it up so that we not only can heat the bed, but we can monitor the power into the reactor, and we can monitor the temperature. And what we actually did is set up the system so that we would figured out how much heat we had to apply just to make up for the natural heat loss from the system. I call that parasitic heat losses. So this system allows us to essentially run a small reactor as if it was an adiabatic reactor. We also use a fluidized bed to mitigate hotspots that might promote undesired oxidation reactions. If you got a hotspot, you may change. Again, you have different activation energies, and you may end up consuming products that you prefer not to do that. And then we also want to discover what is the minimum equivalence ratio we can operate with in an adiabatic reactor that provides enough oxidation to support pyrolysis reactions. So I'm going to just jump straight to some results that we have. And what I'm going to show here is 2 experiments. They were done in the same, it was a 3.5-inch diameter reactor, and it's a fluidized bed. In the one case, we ran it as a conventional pyrolyzer. That is, we used inert gas, nitrogen, as our fluidizing gas in the reactor. And in the other case, we performed autothermal pyrolysis. That is, instead of nitrogen going into the reactor, we actually ran air through the reactor, and that provided our oxygen. And in this reactor, we found that if we did conventional pyrolysis, we could run less than 5 kilograms per hour through the bed and get the reactor to operate and produce complete pyrolysis, showing here the products as they were distributed from this system. But in the case of admitting oxygen and getting this autothermal pyrolysis, that is, there was no external heat transfer to run the pyrolysis process, we were able to increase the throughput through this reactor by a factor of 3, up to over 15 kilograms per hour. Now you can imagine the first time we did it, we were kind of speechless. We had been working for years running on the order of 5 kilograms per hour through a reactor under conventional operation. And here suddenly we were processing 15 kilograms per hour through the system. And it made us make a lot of changes to our feeder and to our system to recover our products of pyrolysis. Now, one thing you'll probably be saying, well, okay, up here, you're getting different product yields. We're showing the heavy ends, and I'll talk about what's in our heavy ends later, but it's got our most valuable products. We were getting about 30% yield of heavy ends from this system. Whereas for the oxygen system, you'd say, I'll bet you're going to lose some yield. And in fact, we lost about 2% yield due to the oxygen in the system. But to us, that was an incredible, worthwhile loss if we could run this reactor autothermally. And in fact, I'll show you that in some cases, we had very little loss of our bio oil in the system. So this brings the notion of what is this impact? So it's clear if we don't need to build heat transfer equipment into the system, we've got a much simpler system. But there's some other advantages as well. This is the notion that we have been limited in conventional pyrolysis by heat transfer. It has not been chemical kinetics that's determined what the size or what the rate we can process material in the reactor. It is simply the rate that we can get heat into the reactor. I think that is true of virtually every pyrolyzer that has been built based on the conventional design. And what we've got to realize is happening here is, I like to show this analogy of what's happening. So if we do a autothermal pyrolysis, this is the blue line, the throughput versus the diameter of the reactor, this is actually a cubic increase. Throughput scales as a cube of diameter. This red line is the conventional pyrolysis. And this is from just putting nitrogen through the reactor, and the throughput scales as a diameter squared. I define the intensification of our process as what we can achieve in autothermal processing rate to what we can achieve with conventional processing. And you can see that the bigger and bigger the reactor it gets, the larger the intensification that we can achieve. We've been operating way down here, and we get a factor of 2 or 3 intensification. You can see a very large intensification. And the explanation is simply, as the reactor gets bigger, it gets harder and harder to get heat transfer into that reactor, and that is a surface area to volume ratio. Let's take a look at the elephant. Why is an elephant virtually hairless and a mouse is very furry? Well, this elephant has a very small surface area to volume ratio. So it is relatively difficult for it to lose heat as well as to get heated up. And that means it doesn't need much of an insulation layer. Whereas this little mouse has a tremendous surface area to volume ratio, and that fur is on there to reduce the rate that it loses heat, or for that matter, to gain heat. And we're seeing this same phenomenon describing this intensification that it takes place here because of this scaling result. This means for a reactor of a given size, we can get many-fold increases in the amount of biomass we can put through the system. We are not limited by heat transfer in the autothermal system. This also impacts the cost of the pyrolyzer. So here I'm plotting reactor cost, relative cost, versus the throughput measured in tons per day. And we see that for a conventional reactor, it scales linearly. So there's really no economies of scale associated with a conventional pyrolyzer. And yet for the autothermal system, where we have liberated ourselves from heat transfer limitations, it scales more like a 2/3 law, the type of scaling law we typically think of many kinds of chemical reactors that are not limited by heat transfer. And this has tremendous ramifications in its cost savings for the system. So I'm going to turn to the second issue, the second heterodoxy, and that is the notion that we shouldn't be able to produce sugars from pyrolysis. You talk to any biochemist, they'll say, there's no way you're going to get sugars from fast pyrolysis. Yes, you've got cellulose, you've got hemicellulose, and yet you don't have enzymes in the system. In fact, all your heat is going to do is destroy the sugars that are produced. This slide is to show that many researchers have demonstrated this over the past, and this is some work we did years and years ago with different kinds of sugar compounds, glucose, cellulose, we use some starch. And what we see is that the yields of levoglucosan, which I mentioned earlier, it's a slightly dehydrated sugar. We'll refer to it as an anhydrous sugar, C6H10O5. The yields of levoglucosan are not very impressive for some of the smaller molecular weight compounds, but when you go up to large polysaccharides, we get yields approaching 60% sugar. And even the starch was around 50%. And you can do that in the laboratory. And it raises the question, so why aren't we seeing these kinds of yields of sugar when we actually do large-scale pyrolysis of lignocellulosic biomass? Now, my next slide addresses that. Turns out that all biomass contains some level of alkali metals and alkaline earth metals. I'm going to refer to that as AAEM. And these are really powerful catalysts. Now, catalyst engineers have known that for years, but it also is a catalyst associated with the fragmentation of pyranose rings and furanose rings in the biomass. So we're seeing here just tiny amounts of addition of salts. So what we've got here is we're going to look at the yield of levoglucosan during pyrolysis as a function of the amount of particular salts added. And these are being added at millimoles per gram of cellulose. And we'll break these down into two sets of curves. The dark curves are alkali metals, and the light symbols are alkaline earth metals. And we see just small, tiny additions of these salts dramatically kill the yield from 60%, they go down to 20% or lower. And by the same token, instead of getting sugars out of our reactor, we get light molecules that are less valuable. Furfural, yes, does have value, but I prefer to be producing levoglucosan. And so these are the breakdown products of this catalytic destruction of the sugars in our system. And as I said, all biomass contains these alkaline earths, so it would seem like we have very little prospects for pyrolysis producing sugars. But you might say, why don't we just simply wash all that metals out? And the answer to that is, yes, you can do it. Researchers years ago showed you can do that. We published some papers on that. But the problem is the cost of washing all of that alkali out is very expensive. Again, look at this curve. We can't leave virtually any metals in there, or we will degrade our sugar yields. But we came up with another solution shown on this next slide. What we did is we treated our biomass before pyrolysis with different kinds of acid. So we did acetic acid, formic acid, and then a series of mineral acids. And we looked at that pretreatment. The goal of this pretreatment was actually to tie up the alkali and the alkaline earths in a stable form, thermally stable form, so that during pyrolysis, they were no longer catalytically active. We'll refer to that as passivation of these metals. And so we would add mineral acids or carboxylic acids at levels, molar levels comparable to the molar levels of these metals in the biomass. And this is what we found. We break this results. This is the weight of biomass as a yield on a weight of biomass basis. And we look at the different products. So here's light oxygenates, here's anhydrous sugars, here's furans, and then phenols are grouped. And we see that these different acids didn't have much effect on phenol production, and that comes from the lignin in the biomass. But what we did see is a switchgrass control, untreated, we were seeing 17 weight percent of light oxygenates produced. And there wasn't much effect from using, shall I say, carboxylic acids. But when we started adding mineral acids, with the exception of nitric acid, we saw a dramatic reduction in these light oxygenates and a very dramatic increase in the sugar production, the anhydrous sugars. Here we're showing a 10% yield of sugars on a biomass basis. And we saw some increase in furans in this case. So we were seeing our ability to dramatically increase by a factor of 6 to 8 the increase in our sugar production by this mineral acid pretreatment. This did not wash the mineral acids out. It simply put enough acid in to passivate the minerals. And this gives us something we call process intensification through Pi sugar production. So I'm plotting here the volumetric productivity of sugar from cellulose. And this is measured on grams of sugar produced in the reactor, per liter of reactor, per hour. And I'm comparing this to enzymatic hydrolysis. I'm plotting this versus time. These different curves shown here at the bottom, colored curves, solid curves, are different levels of enzyme loading. And we see as we go to higher enzyme loadings, we get higher volumetric productivity, and the longer time gives us actually a reduction in productivity. We get higher yields, but our productivity goes down because our time is going up. I'm plotting here as a dashed line the volumetric productivity for sugars from solvent liquefaction. This is based on work done in our own lab, and also pyrolysis done in our lab is this red dashed line. Now what you're seeing is this volumetric productivity of sugars is a logarithmic curve. So we're going from less than 10 grams per hour to levels that are as high as 60 or 70 grams per hour. And in the case of pyrolysis, this is up to, I think this is around 3,000 grams per hour per liter versus less than 10 grams per hour per liter from enzymes. So this is what I call process intensification. Granted, our yields are not as high as enzymatic hydrolysis yield, but we can build much smaller reactors that produce much higher quantities of sugars from this approach. I want to turn to the next issue. It's this bio-oil traditionally is collected in a single pot. You quench, you cool the products, the vapors, and they all end up in the same pot. And my concern about that is if we are trying to produce something as valuable as sugars, we don't want it mixed with the acetic acid or the phenolic oils. We would like to be able to separate them. So what I'm plotting here is saturation pressure versus temperature. These curves here are the saturation curves for different components in bio-oil. Over here, we're showing levoglucose in this light blue. This red line is the saturation curve for phenol. And I believe, let's see if I've got this right. I believe this curve right here, this darker blue, is for water. And these straight line, dashed lines across are the different actual vapor pressures of different components in the bio-oil stream before it's condensed. And we can see that there's a high vapor pressure for water, and there's lower vapor pressures for phenol and levoglucosan. But what we could see is if we take this water vapor concentration, so to speak, down to the saturation curve, we see we have to drop the temperature to about 50 degrees centigrade before we actually start condensing water. But the boiling point of levoglucosan is so high, despite its relatively low concentration in the vapor phase because of its high molecular weight, they should start condensing at about 200 degrees centigrade. So this gives us a notion we could come up with a scheme to actually condense products according to their vapor pressure based on their boiling point and separate them out separately. And we've done this with what we call a fractionating bio-oil recovery system. And this is shown here. We are able to cool our condensers at different temperatures and condense them out at different temperatures. So this is work we've done several years ago, but it has been very important for our ability to recover sugars in our system. Well, it turned out we're actually condensing sugars and the phenolic oligomers together. And so we have asked ourselves, how can we separate these phenolics, which is a heavy viscous material, it's not water soluble, by the way, from the sugars, which are water soluble. I'm a home brewer, and I got some inspiration from brewing beer one day where I realized the way I get sugars out of grains, out of malts, is to actually use a hot water rinse to separate the water soluble sugars from the water insoluble grain hulls. We're doing the same thing in our laboratory with the heavy ends of oil, using hot water to scrub out the sugars from this system. And it's been very successful. I want to show a picture of our pyrolytic sugars. And you say, well, it's an interesting color. I would have thought sugars would have been clear. And what you're seeing is some contamination from some partially soluble phenolic compounds, which give it some color. This color is the same kinds of compounds that give color to wine, for example. Although it's kind of a pretty color, we don't want it in our sugar stream because they actually are fermentation inhibitors. And we've discovered the same resins that are used to adjust the color of wine and the phenolic content of wine work very well for this sugar that we're producing from pyrolysis. And we have been able to separate out pyrolytic sugars from this contaminant and getting up to 99.5% purity, separate out the phenolic monomers from that as a separate product. And we've also been able to take this pyrolytic sugar, which is a combination of different sugars produced during pyrolysis, and get a pure levoglucosan product from that. This material is extremely valuable as a platform chemical. Now, I don't have time to get into that too much. I'm going to focus more on some of the issues that we've dealt with during pyrolysis. So here's the question I want to answer. We have been very successful in doing this acid pretreatment to get very high yields of sugar out of biomass. But we also found that the char that we produce, instead of being a fine powder, is agglomerated char. We want to be able to prevent that. And that meant we needed to understand why an acid pretreatment was causing agglomeration. And this agglomeration actually occurs if you had used an acid wash to get all the alkali out. It's not the fact that we have an acid in there, it's something else. And this is what we've discovered has taken place. When we do the acid pretreatment, it does put protons into the biomass, but it's pulling the alkali out of the biomass and forming a stable salt with the sulfate. That's sulfuric acid we use in our pretreatment. And this is why we are getting high sugar yields, is we've got the alkali out of the cellulose, so it can't catalyze pyranose ring fragmentation. But it's been something we've learned recently, is that that alkaline earth metals are also catalysts to depolymerize the lignin and volatilize it. And so we have slowed down the depolymerization of lignin. And so all it's doing in the reactor is melting and sticking together, sticking on the sand and form this agglomerate. So that's a problem that we need to solve. And what we need is an ionic compound which still causes passivation of the alkali. We want the anion in our new compound to passivate the alkali, but we want the cation to selectively catalyze lignin depolymerization. We've discovered, and we want it to be water soluble because it needs to diffuse into the biomass. We have found that ferrous sulfate can do this. So I'm going to show you what it does. In this case, the pretreatment with ferrous sulfate pulls the alkali out of the biomass and forms this stable salt. So it protects against cellulose, our sugars from fragmenting. But it puts iron into the biomass instead of protons. And this iron is a catalyst for the lignin depolymerization. So this change in pretreatment has resulted in a fine powdered char instead of those agglomerates, still producing the sugars that we produce from the acid pretreatment. So this has solved two problems for us. We've tested this ferrous sulfate pretreatment over a lot of different kinds of biomass, and it works very well in most instances. But we're still seeing sugar yields that are no higher than 60%. And this is a problem that we've only recently investigated in detail. And the story there is still not completely solved. We understand what's happening, but we haven't come up with a solution. So I'll detail the problem on this slide and then hope somebody in the audience comes up with a solution for this. When we pyrolyze cellulose, we would like it to crack to form oligosaccharides, and then to have an unzipping at the end of this cracked chain, releasing the end pyranose ring as levoglucosan or anhydrous sugar. This is a reaction we want to happen, and it happens. But there's a competing reaction, which is the fragmentation of these rings. And even though we've removed all the alkali and slowed down that breaking fragmentation of the rings, it is still happening. And we end up with these light oxygenates. What we need, we've eliminated the catalyst over here for ring fragmentation. What we need is a catalyst that will selectively increase this unzipping reaction and produce more levoglucosan. If we could do that, we could go from yields of only 60% to 100%. I'm looking for some help in this respect. But we've made enough progress that we've gone ahead and developed what we call a Py Refinery. A Py Refinery is going to take lignocellulosic biomass. We've done this both with switchgrass, corn stover, and wood. And we'll apply our process of autothermal pyrolysis and our process of selectively fractionating recovery and get four major products. One is the sugars we've talked about. One is the phenolic oil from the lignin. The third is going to be the light oxygenates, which is dominated by acetic acid, and then char. And for our first generation facilities we're building, we're interested in the sugars being converted to ethanol, the phenolic oil being used either as a marine fuel substitute, or we've also developed a bioasphalt from it. This unrefined acetate, right now we're just using it for thermal energy. We're not even condensing it to this liquid I've shown, but keep it as a vapor, which has heating value, and we get in-plant thermal energy from it. And of course, the biochar has lots of interesting applications that I won't get into but those are used as a soil amendment, as a carbon sequestration agent, And more recently, we've been looking at it as an activated carbon. The economics of pyrolysis are looking good right now, right? What I'm showing here is the sugar production cost, dollars per megaton. This grayish area is the range that has been achieved with enzymatic hydrolysis using enzymes to break down, to hydrolyze the sugars. And this is showing what we're achieving for different scenarios of prices of the biomass ranging from $40 a metric ton to negative values if it was a waste stream that had a tipping fee associated with it. We're also looking at different values for the phenolic oil from the lignin. If it's produced, turned into a bioasphalt, it would be worth $500 a ton. For a fuel, it would only be probably worth $50 a ton. And we're seeing what the kind of sugar prices are. And if we can sell it as bioasphalt, we have very competitive prices for the cellulosic sugars compared to what can be achieved from enzymatic hydrolysis. This is an area we're still working on, but we have moved forward in doing a demonstration project of autothermal pyrolysis in the state of Iowa. It will be a 50-ton per day unit. It is going to be located in Redfield, Iowa. It's privately financed. We have a company in Ames called Frontline Bioenergy, not far from Iowa State University, that is doing the engineering, procurement, and construction for this project. And the goal is to use corn stover for production of bioasphalt and biochar. This will be followed by a project in California funded by the California Energy Commission that will look at converting wood waste in Northern California into drop-in biofuels. Now, interestingly, the same plant will be used in Iowa and California. Now, how's that done? Well, I haven't had time to talk about it much, but we are developing our demonstration project along the ideas of modular systems. So each one of these modules shown here stacked next to each other or connected to each other represents what could be fitted in an ISO container on a flatbed truck. And so the notion is we will build this in a factory. It will be shipped as modules to Redfield, Iowa, put together, run for 6 months, then taken back apart and trucked out to California for this second project. So that is my presentation. I've got lots of acknowledgments. I want to acknowledge the creative and dedicated efforts of a long line of graduate students. One of them pictured here, you may recognize him. I also want to thank several funding sources ranging from federal agencies like the U.S. Department of Energy and the U.S. Department of Agriculture, as well as a number of private companies, ConocoPhillips, Phillips 66, and ExxonMobil. Our current work on this notion of a modular system is funded by the U.S. Department of Energy's Advanced Manufacturing Office. This is part of what's called the Rapid Institute that Iowa State University is part of. And we also are indebted to Stein Seed Company for financing this first demonstration project. And with that, I would be happy to answer any questions. I forgot to show this slide. Okay. Many thanks to Juan for his part in our programs over the years. So,
no, thank you, Dr. Brown.
You haven't changed a bit, have you? So,
just a little.
So with that, I'd be happy to answer any questions.
Well, thank you very much, Dr. Brown. We are open for questions. I think
we have 2 questions that were made through the chat. The first one from Rocio Sierra in Uniandes. What is the difference between autopyrolysis and gasification?
Excellent question. We have learned there is what's called autothermal gasification, and this is the notion instead of trying to externally heat a gas fire that you add air or oxygen and get those reactions to occur. The difference is gasification is ideally a thermodynamic equilibrium process. So you don't have to worry too much about the kinetics of the process as long as things occur fast enough in your reactor. They're all going to be light gases. In the case of autothermal pyrolysis, we want to preserve our non-equilibrium products, which is the bio-oil. And so now we've got this balancing act of what are the kinetics that are going to drive the oxidation processes, what's going to get oxidized. We can't simply do a thermodynamic equilibrium calculation and say, this is what's going to happen. We really need to know the kinetics. So think of it as gasification as being an equilibrium process versus pyrolysis being a strongly non-equilibrium process with the goal of producing mostly liquids as opposed to mostly gases.
Okay, we have another question here. It says, for separation, it is necessary to take into account the effects of mixtures on saturation pressure of the different compounds. Have you seen that? It looks like you just look for saturation pressures of pure substances.
Yes, and that is I've clearly got an expert on the line that has more expertise on the subject than me. That was for illustrative purposes and actually helped us think about the design. In practice, that we found that it was very difficult to achieve much separation, and that has to do with the viscosity of these phenolic compounds that we produce. There's actually oligomers. We think what's happening is we condense phenolic monomers that have appropriate boiling points. They then start condensing to larger oligomers. So it's a difficult process, and that's why to date we have not tried to separate the sugar, to condense out separately the sugars from the phenolic oils. We just do a heavy ends. So yes, it is a difficult process. We hope in the future to do better separation online during the condensation process, but right now we do a lot of it post condensation.
All right, we have another question from one of the professors, Jose Mora.
Okay, hi, Professor Robert, nice to meet you. I have a question about the slide number 21. It's about the question that you say about why don't we get more than 60% in the levoglucosan specifically. Yeah, I have seen some paper about this situation, and they say that we can put alkoxy group in the eastern of the cellulose. And I have some paper about in the green chemistry journal that say that we can obtain 90%. We can looking in the acetal group, transforming the hemiacetal group in an acetal group. What is your opinion about this possibility?
I would be interested in learning more about that because in principle, you could put some kind of protecting groups in. I remember seeing some papers that talked about trying to do, I won't call it pyrolysis, but using a chemical process to try to preserve the sugar rings. And that's what we're trying to do. How can we slow down the fragmentation of those rings? Again, I'm not going to be the expert. That's why I said I'm looking for somebody to solve this problem as a practical basis. Really what it is, we've got this competition between unzipping and ring fragmentation. And we've shut down ring fragmentation as much as we can. What we need to be able to do is to catalyze this unzipping reaction, I think, or protecting the groups in some fashion.
Yeah, it's a protecting group. Okay. Okay, thank you.
I look forward to your upcoming publications on the subject.
Okay, thank you.
One more question here. It says the presence of air and also possible active metals could enhance the production of CO and CO2. Have you seen that?
We just published a paper on that. I don't think I think it may still be in press, but it was accepted 2 weeks ago and we just sent the proofs in last week. It's been a real interesting to see how the presence of the alkali in the char can actually improve our pyrolysis process. We're finding autothermal pyrolysis actually works better for corn stover than it does wood, for the very simple reason there's more alkali metals in the corn stover, and it accepts the oxygen and then transfers it to the char, and we get, instead of getting a lot of CO production, we get enhanced CO2 production, which means we get a lot more energy released for that mole of oxygen going into the system than simply producing CO. So thanks for that question. It's that paper should be out shortly. I'm trying to remember which journal. I think it's the Chemical Engineering Journal that we published that in.
Thank you very much, Dr. Brown. I think you might remember this name, Juan Daniel Martinez.
Mm-hmm.
Can Juan Daniel open his mic and ask his question, please? Well, I think we have an issue with that. Well,
is it about auger reactors? So.
Yes, it's basically, yeah, it's related to that. So he's asking, do you think autothermal pyrolysis could be performed by using other kinds of reactors, maybe auger reactors, instead of bubbling fluidized beds?
Well, I put a student to work on that, and we switched his projects because we decided it was a big problem. We would love to see it done in an auger reactor. If it's done in an auger reactor, though, we have been using fluidized beds as if they're a continuously stirred tank reactor. And if you think about an auger reactor where you put all the oxygen up front with the biomass, you will get a hot spot where you will over-oxidize your biomass. So in other words, up front, the equivalence ratio will be really high, and then downstream, it'll be too low. So I think what you're going to have to do with an auger is be able to inject oxygen along the length. Here, I'll try to show that, along the length of the thing. And now it gets to a control issue. And I decided it was just too hard a problem for a master's student. It's going to require some clever modeling to decide out how do you distribute that air with the kind of mixing that occurs in an auger reactor.
Thank you very much, Dr. Brown. We have a question from Yanet Villasana. I would like to know if you have tried basic biomass pretreatment instead of acid pretreatments. Which of the methods or process demand more monetary costs for the generation of energy?
Okay.
She's from Costa Rica.
So
I think
a base treatment is often used with biomass as a pre-treatment, especially in solvent liquefaction. And there it works extremely well. But the goal, the problem with the alkali addition is it will also, if you did it under pyrolysis condition, you're admitting more potassium or sodium or calcium to the system, and you're going to destroy sugars. And one of my major goals is to be able to compete with the biochemist in producing sugars from biomass. So I think the alkali base treatment is a non-starter in terms of what my goals for the system would be. The acid treatment was nice because sulfuric acid is not particularly expensive. But where we ran into troubles was it encouraged this char agglomeration. And that required us to really scale back on the rate that we fed biomass in. So all the intensification we gained with oxidation, autothermal operation, we lost with the acid pretreatment. That's where this new ferric sulfate pretreatment has really been a lifesaver for us. It's really game-changing in that ferric sulfate is not actually much more expensive than sulfuric acid. It's a byproduct of steel production. So it's not very expensive. And we're finding it is cost effective. Our TEAs that we're doing do not find that it is an expensive addition to the process.
Thank you very much, Dr. Brown. we have another question. What do you think is going to be the role of the biorefinery and biomass utilization in this post-pandemic scenario?
Well, I'm going to say in the post over-enthusiasm about bioenergy of a few years ago, I was sorry to see, actually going back to 2006 and 2007, the irrational exuberance for bioenergy. I think it has great potential, but too many promises were made back in 2006 of, in 5 years, we are going to be producing billions of gallons of cellulosic biofuels, and we're going to be converting lignin into new products that we could never imagine. It was I just knew that if you went in the literature, the technology was not ready to do that. But what I do see emerging, so we've lost a lot of interest actually in bioenergy in the United States. Today, when the press talks about renewable energy, they specifically exclude bioenergy. And there's lots of reasons for it, including, okay, you promised once and didn't deliver, so we're not going to listen to you anymore. But I do believe post-pandemic, we will see increasing calls for a carbon tax. And bioenergy, especially in South America, but also in North America, has tremendous potential if people will understand how to do it sustainably. And something that bioenergy can do that wind turbines and solar photovoltaics cannot do is carbon removal. We can come up with schemes based on biochar or sequestration of CO2 that actually remove carbon dioxide from the atmosphere. I just listened to a story on The Economist last week where it was, they were projecting, it was a make-believe story about carbon removal in the next 30 years. And bioenergy was one of the two that technologies they were looking at in this story about carbon removal. So my view is carbon removal is going to drive a lot of the interest in bioenergy in the coming years. And that includes gasification, where you sequester the CO2, and pyrolysis, where you sequester the biochar.
Thank you very much, Dr. Brown. So I think with no further questions, we can switch to Daniela.
Well, I have one last question before I finish. So, Dr. Brown, in what residence time range do you work for the fast pyrolysis for the fluidized bed? What times do you use?
So that's a great question, because I'm finding all of the published literature on pyrolysis assumes kinetics that are much faster than what we actually see happens in a pilot scale, a continuous reactor. And in the case of conventional pyrolysis, that's because heat transfer is rate limiting.
Right,
so
we found it out also.
Designing based on kinetics at all, you should be basing it on heat transfer. In the case of autothermal, I'm also finding that the kinetics are faster than what we actually observe in, if I were to use the kinetics to design my autothermal, the kinetics are too fast. And I think what the case there is, many of the kinetics are focused on the devolatilization step. And we know devolatilization is finished in a second or two. And yet, if you really look at the char that's left over, it will smolder, is the word I'll use, for up to 20 minutes. And we're finding that the residence times are probably closer to 20 to 40 minutes of the residue. So it goes in, you get a lot of volatiles off real quick, but ultimately the size of the reactor is going to be determined by how long it takes to get all those volatiles released, which is a much slower process. So even autothermal, we're finding residence times are probably about 20 minutes or so. We have actually, in our most recent paper published on autothermal pyrolysis of corn stalks, corn stover, we measured the bed loading of char in the reactor. And it's a pretty heavy loading. And that's telling us it's still in the reactor and it's reducing the ability to shove more biomass in until we can process that material and get all those volatiles off.
Of course. Wow, very interesting. I was thinking about smaller than 1 minute, but residence times between 20 and 40 minutes are quite long. And it's true, we have also found that heat transfer is limiting the process and not kinetics.
Right.
So it's very, very interesting. And I think we will be able to work with a lot of your information to improve our experiments on pyrolysis on our small pyrolysis groups that are working at USFQ. So thank you very, very much, Professor Brown. It was a fantastic talk. It was very illustrative. It was very clear. I think everybody liked it a lot.
Thank you,
so thank you very much for this very interesting talk. And I hope we can see you on person on next occasion. Let's hope that pandemic and all the sanitary emergency gets over fast, and so we can meet someday in person.
Thank you. And if I could add, I hope everybody listening will give some thought to going to autothermal pyrolysis. Even if you think sugars is a pipe dream, the autothermal pyrolysis, it is such a simpler reactor to build, and the throughput is just incredible. It has allowed us to build this 50-ton demonstration unit, which is only it's a 1 meter diameter fluidized bed to process 50 tons per day.
It's amazing.
I hope everybody will give some thought to this simple change to your pyrolyzers and run them autothermally.
We definitely will put some air in it. Definitely. No, it was fantastic. And well, so thank you very much again, Professor Brown. And with this, I would like to invite everyone to our next talk. Our next talk will be, let me share brief my computer. I will take you a little bit, excuse me. So our next talk is on the biochemist. So we will have a talk about anaerobic digestion from Professor June from the Technische University of Berlin. And he will talk about anaerobic digestion and the requirements and challenges for feedstock flexible operation. And the third talk will be also again about bioprocesses. And then finally, the fourth talk held by Professor Kumagai from Japan will be again pyrolysis. So we are having an equilibrium so far, two talks about thermochemical processes and 2 talks about bioprocesses. And so we have a good equilibrium between both technologies. So with this, I want to thank you again and wish everybody a nice weekend. And well, and let's hope we meet in 3 weeks. So with our next talk. Thank you very much, everybody. Thank you very much, Professor Brown. Bye, everyone.
Thank you. Thank you very much.
Bye. Thank you, guys. Thank you, Dr. Brown.
Bye.
My pleasure.
Have a good weekend.
Bye, Shago. Bye, everyone.
Thank you.